So welcome to the convection heat transfer course. Okay, so this will be the first lecture. So before I go on and start describing that how we will approach this entire topic, let us have a very brief background that what is convection heat transfer per se. So those of you who have taken courses on fluid mechanics know that fluid mechanics is basically a transport of momentum essentially. Okay. Now heat transfer, whoever have not taken convection know that heat transfer is associated with say for example, you may be familiar with problems in conduction. That means you take a rod, you heat one end of the rod, and after some time you feel that the other end of the rod becomes heated, right. So somehow the heat has conducted through this solid medium, right, and you have felt its effect. Now that is of course quite relevant in objects which are basically not moving, that means solid bodies, say for example. It can also happen in fluids nevertheless, but usually these are not associated with movement of the medium per se. So by movement of the medium I mean that there is no transport that is happening, okay, between the two ends of the rod except through the process of diffusion or conduction that takes place through the rod. Okay. So it is conduction that most of you are actually familiar with. Convection may not be all that apparent, but the fact that convection is an important phenomena, if you look at any application in the world, right, anything, and that can range from microfluidics all the way up to large gas turbines. Okay. It can encompass, like for example, biology, fields in biology, okay, to fields in fabrication, manufacturing, wherever you go, you will find that convection heat transfer is perhaps the most important mode of heat transfer that is available, right. Now the other two modes of heat transfer, the conduction and the radiation, they are also important, okay, but convection is actually encompasses both conduction and advection. Advection is related to the motion, right. So these two combined gives that term the convection. And this is one of the most important modes of heat transfer, which is commonly encountered in all spheres of life, in all important applications that you are going to encounter with, right. So in this particular course we are going to talk through that what are the different aspects of convection heat transfer. For example, we will first do the conservation equations, that is there is a conservation of mass, momentum and energy. Then we will shift gears and go and look at some canonical problems, like for example flow over a flat plate, okay. Then look at the classes of solutions, that how we can solve a problem, okay, for external flows. Then we will go on to internal flows like flow through pipes and other things. Then we are going to move on to natural convection. Natural convection, we will see what natural convection is in due course, and then we are going to look at the turbulent modes of heat transfer. And if time permits, we are also going to focus a little bit on the small scale nature of heat transfer as well through convection. So let us start. Okay, so if I start jotting down some of the points, okay, so the transport of heat, if you look at the board, or the transport of heat, okay, here for example there is a blob of fluid, let us call that fluid blob 1, okay. It moves to another location, okay, which is called say location 2. So basically what it does is that fluid blob 1 transports whatever energy that it carries to the location 2, right. So in this case the energy is in the form of heat, okay. So this transfer from 1 to 2, okay, has happened due to advection, right, advection or motion of fluid, correct. Okay. Now if this was conduction, this would have been a rod, say you apply heat to one end of the rod, after some, and you put your palm on this side of the rod or some kind of a sensor on this side, you will feel the heat after some time, right. So that would be conduction through the medium, okay, without this kind of a motion that you see over there, right. So convection essentially, as you can understand, it's a much more what we call much more enhanced process, because there is a bulk motion that is involved, Okay. So, it is not a slow process, it is actually supposed to be a little fast, right, compared to pure conduction. Okay. So, unlike pure conduction, right. So, unlike advection slash fluid motion plays an important role. Now, if you look at it from the scheme of things, whenever there is fluid motion, that means there will be a lot of fluid dynamics that will be involved, because first you have to know the fluid dynamics of the flow field, right. Let us take an example. Let us take this example of a flat plate, right. This flat plate, and then there is a flow that is approaching the flat plate. Now, this flat plate, what might sound to be a very, why am I placing a flat plate in a flow field? This flat plate can be, say for example, a gas turbine blade, okay, a heated gas turbine blade which you need to cool, okay, otherwise this blade will actually crack. This is the most common gas turbine, as you know, is the most common form of power generation, okay, which drives the power in a aircraft, okay, or powers your house and all these things. Okay. So, it actually produces 25 to 30% of the world's power, right. So, in a gas turbine, the turbine blades needs to be cooled so that they do not crack and they do not fail, right. So, you can imagine that this may be a heated plate at a temperature T1, and this may be a flow of cold fluid which is at a temperature T0, such that T1 is greater than T0, right. So, what you are essentially trying to do is that you are trying to extract the heat out of that plate, right. Now, if there was no flow, okay, if there was no flow, okay, in the absence of natural convection, this plate would have lost some amount of heat to the surroundings, correct. That would happen, right. That is also happens, say for example, if you place a heated heated rod in an ambient environment with no flow, say for example, you will find that this will cool, definitely it will cool down, because heat will flow from high temperature to low temperature no matter what, but it will take a very long time for it to cool, right. So, in a gas turbine environment, that time scale is something that you cannot afford, right. So, in order to achieve the rapid cooling of a blade, okay, what do? The most common thing is to pass a flow over it. This is the same reason that if you have if say you are drinking tea, right. So, what happens is that you sometimes actually blow air over the tea to cool it down, correct. That is what we normally do. So, you just blow a little air, then you sip the tea, right. Why do you do that? You are basically creating a flow over the surface of the tea. Why? That is because you are trying to create a convective mode of heat transfer, so that you can extract heat at a very rapid rate. So, essentially that is the same thing. If you look at the PPT once again, or in the journal, you will find that this is a plate and there is a flow that goes over the plate, right, with the sole purpose of cooling it, right. Now, in order to describe this particular phenomena, say I as an engineer, I want to know that how this particular plate is going to get cold, right, what will be the temperature distribution in the near vicinity, right, how effective I can actually cool the whole thing. For knowing those answers, right, we have to first analyze the problem. And what is the analysis? First you have to solve what is the flow field, right. That means what will be the flow field? This flow which comes out nice and uniform as it encounters the plate, right, what will be the flow field looks like. Once we know the flow field, then you can use the flow field basically to solve the equation. So, the hierarchy is very simple. First you need to solve continuity, which is basically mass conservation. Next you need to solve the momentum, which is basically your fluid dynamics equation, right, and ultimately you need to solve your energy equation, okay, which if you solve it properly will give you the temperature field, right. Now, normally all these things may be actually coupled with each other, especially these two. What do I mean by coupling? Coupling, I mean that, say for example, take this example that when you actually have temperature in a flow field, the density changes, right, because density is a property which is a function of temperature, right. And the momentum equation we will see shortly has got density as one of the most important terms, right. So, there could be that with energy. So, momentum equation is influencing the energy, that is because you have advection. Now, in this energy equation, the density changes because of the temperature field. This density change once again feeds back into your momentum field, right, and that creates what we call a two-way coupling between the two. That means you cannot solve the two equations independent of each other, but in most of the cases you will find that the coupling is only one way. That means the momentum influences the energy, which it would, because it is a flow. I mean, we will see that the energy equation will have the flow terms, right. So, you need to solve the flow field before you come to the energy equation, right, standard. But we will not deal with situations where the reverse happens. That means there will be energy which will change the density in such a way that the momentum will be altered. Okay, we are going to do natural convection, but there will be some approximations that we will make, okay, where we do not need to deal with this kind of an acute problem, right. So, that's what it is, right. So, the order of things still remains the same. You have to solve continuity, momentum and energy. So, you cannot directly go and jump and solve the energy equation. Okay. In conduction it is possible because there is no flow. Understand the thing. In conduction it is possible to solve the energy equation as is, right. But when you are dealing with convection, you cannot solve the energy equation as is, right. You first have to come through the momentum, right. So, unless you solve these two, there is no way you can actually describe this canonical problem where there is a flow over a flat plate, heated plate. Okay. So, you have to first know the flow field. In this case, the flow field will look like something like that, right. Once you know the flow field, then you can use that to solve the energy or the temperature field, right, which will look something like that. Okay. And once you have those two informations, you can find out that how this plate can be effectively cooled or effectively heated, whatever may be the purpose, right. Okay. So, as a first step, in the first lecture, what we are going to do, we are going to look at the continuity equation first, because our order of business will be, first we will start looking at the conservation equations, because those are the building blocks. Once we have a thorough idea of the conservation equations, then we will move to all these canonical problems, right. Because once we do the canonical problems properly, you will get a feel that what convection heat transfer is, right. And any canonical problem, we are going to solve it in, try to solve it in actually three ways. Okay. One will be the complete analytical solution. That means you can just use pen and paper to solve the whole thing. Okay. As you know that fluid dynamics equations are non-linear. So, solving them analytically poses a very big challenge, but in certain cases you can, okay, especially where the non-linear terms are small or 0, we can make certain approximations, okay, certain special cases. Okay. The second class will be some kind of approximate solutions. So, we will talk about integral formulations and things like that. And the third and the most important thing from an engineering point of view, we are going to spend a lot of time on doing this scaling analysis, because why scaling analysis is important? Because this will enable you to take a pen and paper and essentially work out the physics of the problem and get the correct relationships without going into too much math or experiments, right. So, that gives you from an engineering perspective a great feel of the problem. So, you know that how my heat transfer is happening, right, without spending a lot of time in doing very complicated simulations or experiments. So, that is vital because that gives you a lot of insights. So, essentially this will be the way that we will work out if you look at. So, there will be some analytical approaches, okay. There will be some semi-analytical, which we will see what those are, right, okay. And there will be of course this scaling. So, these three approaches are going to give us a complete idea of each and every canonical problem that we can get hold of, right. But remember, most of the problems in real life will be much more complicated than this. So, that will require perhaps extensive experimentation, or it might actually require complicated CFD simulations, okay. But these will offer you the great insights on the nature of the problem, okay. So that later on when you go to more complicated situations, you have a feel, you have the fundamentals worked out, okay. So, that is the first thing. So, let us look at the first set of equations that we will do. So, that will be mass conservation or continuity. This is important. So, if you observe, let us take any arbitrary control volume. Okay. So, this is a control volume which can have multiple inlet and outlets, correct. So, there can be some inlets, some outlets, that means mass is entering into this control volume through multiple ways, and the mass inside the control volume can be allowed to change. So, that is MCV. So, for a control volume, so control volume in short as CV, MCV by dt, okay, is basically summation of all the inlet mass minus all the outlet mass, correct. So, whatever mass is coming in minus whatever mass is going out, that would dictate what is the change of mass within the control volume, right. This is a very simple thing that you have done in thermodynamics and other cases as well, right. So, there is a lot of inflow outflow. Now, if I make this control volume infinitesimally small, small control volume, okay, let us take this particular picture. This is the control volume, though I have drawn it big, it is actually small, okay, and let us do it in 2D, okay, but potentially this can be done in 3D as well. So, there is no problem, but 2D is easier for people to understand. This length is delta x being a very small number, this length is basically delta y is once again a small number, right. So, what is happening? So, this is a very small control volume with delta x, delta y, that kind of a thing. Okay. So, what happens is that mass enters into this control volume through this phase, leaves this control volume through the other phase, right. Similarly, mass enters this control volume through this phase and leaves the control volume through this phase, right, phase. So, this particular phase, the mass can be written as rho v, okay, evaluated at y, okay, into some delta x, where v is basically the velocity in the y direction, right, v velocity in y direction, correct. So, you can understand this is the mass rho into v, okay, should give you the, and then multiplied by delta x, and this is a unit volume. So, you can basically the other phase, the 3D part of the phase is basically 1, okay. So, and what is leaving out, this will be still rho v, but it is evaluated as y plus delta y, okay. So, these two v's are not the same, one v is evaluated here at y and one v is evaluated at y plus delta y, this is also multiplied by delta x, correct. So, similarly on this phase what will happen, let me write it here, is rho u, right, evaluated at x into delta y, right, and what is leaving on the other side is rho u evaluated at x plus delta x, okay, into delta y, correct. Okay. So, this is the situation, right. So, once again u is evaluated at x, u is evaluated at x plus delta x, these two u's are actually different. Okay. So, coming back now, if we write all the inlet mass now within this control volume, right, what it will be? It will be rho u in evaluated at x into delta y, correct, plus rho v evaluated at y into delta x, correct. These are the, this is the mass that is entering inside the control volume, as you can see from the arrows, right. Then there are mass which is going out, which is m dot, right. So, that will be rho v evaluated at y plus delta y into delta x, correct, plus rho u into x plus delta x into delta y. Okay. Let's put a marker here so that you do not get confused. Okay. So, this is the inlet and the outlet mass, right. Now, how do we evaluate terms like this? That is a question, right, because we have to somehow cast it, right, in order to get an expression, cast it in some familiar form. So, what is the commonly used thing that we use is first order Taylor series expansion, okay, Taylor series expansion. Okay. So, what does the expansion look like? Let us say for example, you take rho u at x plus delta x, right. This term you take, you basically expand it around rho u at x plus, this is a first order only, right. So, you know what will be the truncation term, rho u into delta x, correct. So, that is the first expansion. So, similarly you can work out for rho v y plus delta y, right. You will first have rho v evaluated at y plus d by dy, right, okay, into rho v into delta y, right. So, that is the expansion of each of the term, right, got it. So, this is the first order Taylor series expansion, first order only. So, we are retaining the first order term only. So, when you evaluate the exit velocity, you can expand it around the inlet velocity plus whatever is the slope. Essentially this is the gradient, the second term is essentially the gradient, right, of the whole thing. Okay, good. So, now that we have established this, now the job becomes very easy, so to say. So, that means when you actually have in m dot minus m dot out, right, you have to evaluate this, right. So, what we do, let us assemble all the terms together, that is this is x plus rho v y delta x minus rho u evaluated at x into delta y, okay, minus d by dx rho u delta x delta y minus rho v at y delta x minus rho v by rho y rho v to delta y into delta x, got it. Okay. So, as you can see, most of these terms will actually drop out, okay, because you are expanding it, okay, these terms will drop out, okay. So, you will be left with an expression which will be rho u delta x into delta y minus rho v into delta y into delta x, right. So, that will be the expansion. Now, so this actually tells you what is the mass going in, mass going out. What is the rate of change of mass within the control volume? That will be given by this rho delta x into delta y, right, because the other side of the control volume we always said it was unity, right. So, this should be now equal to, okay, equal to this particular term, okay. So, now so if you now transfer the terms on the right hand side to the terms on the left hand side, and if you take off the delta x and delta y out, you will find this expression takes this nature, right. If you want to write it in 3D, so this is actually strictly in 2D, right. If you want to put it in 3D, so that will give you right, where this is the additional term due to the 3D effect, okay. So, where z is the other direction, okay, z or z is the other direction, and w is basically the velocity component in the z direction, okay. So, based on this, this is what your continuity equation looks like, okay, clear. So, this is the what the continuity equation looks like, right. So, you can write it in a little bit more compact way, okay. So, you can also write it by the using the material derivative, this is the most compact way of writing the continuity equation, got it, Okay. So, if you expand this, you will basically get what I wrote for the 3D or the 2D depending on what your flow configuration is. So, this is the compact notation. Okay. Now, for incompressible flow, things become a little bit more simple. Okay. What is incompressible flow? That means incompressible flow means that there is no density change, right. Okay. So, when there is no density change for an incompressible flow, all we get, this reduces to this equal to 0, right. In other words, if we cast it in a proper form, this means in 2D you can write it like this. Okay. This will be the most common form that we will use, right. So, this is in other words, it says that the volumetric dilatation is actually equal to 0. So, this is the most common form of the equation that you will get, du dx plus dv dy is equal to 0. If there is a third dimension, that will be plus dw dz will be also equal to 0, right. So, this is incompressible, right, when density is not changing, okay, with the flow field. Okay. So, this basically completes that from this continuity equation, all that in most of the flows which are kind of incompressible, we are going to deal with mostly incompressible flow, you will find that this is the most common form of equation that you will use. That means there is no volumetric dilatation of the flow field. Okay, there is no volumetric dilatation of the flow field. That is what this actually essentially means. Okay. So, in the next lecture, we are going to look at the situation in which we will look at the conservation of momentum now. Okay. Previous lecture we did conservation of mass and we looked at what is convection heat transfer all about. In this particular lecture, we are going to look at conservation of momentum. Okay. Because that was the next step, as I said. Now that we know what conservation of mass is, now we move on and see how the conservation of momentum will look like. So, conservation of momentum, right. So, we look at the same control volume, there is no need to change that control volume, right. This control volume is still the same, right. So, what will be the conservation of momentum for this control volume in any particular direction? Now, the direction becomes important because mass was a scalar, this is a vector quantity. So, you have to look at actually 3 directions. Okay. If it is 2D, you have to just look at 2 directions. Okay. So, first term is essentially okay, what we call the rate of change of momentum within the control volume, right. That will be equal to all the external forces that are acting in the control volume plus whatever is the momentum in minus whatever is the momentum out, right, where n is basically any direction of your coordinate system. That means, it will be x, y, z essentially. If you deal with spherical coordinates, it will be something else, right. So, in essence, this particular form of this conservation equation is basically Newton's second law of motion, nothing like that, nothing more than that, right. So, there are some external force terms, okay. There is a rate of change of momentum within the control volume and then there is momentum in and momentum out. So, that is Newton's second law of motion, which is basically F equal to ma, right. Okay. So, let us look at it from a control volume approach like what we did earlier. Okay. So, we look at the same thing, let us look at the x axis. Okay. Let us take the x momentum equation essentially, okay, and the y and the others will just fall into place. If I do one, you can do the others essentially. Okay. So, let us look at that what are the different types of forces that are acting on this particular control volume. Okay. So, on this face, if you look at it, okay. So, there is this normal stress which is acting on delta y face. So, once again the nomenclature remains the same, this is still delta y and that is still delta x, delta y, delta x, right. Okay. So, similarly on this side of the face, okay, what will be the, once again using that same Taylor series expansion analogy, you will get this. Am I right? So, that will be the same thing. I am not going through the details, it will be once again sigma at x plus delta x. When you expand it, you will get this particular form, correct. So, the two faces in the x direction, these are the normal stresses. Okay. Then what other form of stress do you have? You have the shear, right, the shear stress. So, that will be tau y x into delta x is acting on the x face. Similarly, on the top you have tau y x, okay, plus d tau y x by dy, right, into delta y. Once again that same Taylor series expansion into delta x, right, on the top, okay, same thing. So, as you go, so it is expansion around y because you are going across the y face, right. So, these are the surface forces that are acting. Okay. So, forces can be of two types, one are surface forces and one are body forces. So, similarly you can have a body force which is represented by x, okay, multiplied by delta x into delta y. Okay. So, that is a body force. So, most of the useful examples of body force are gravity. Okay, gravity is one example of a body force. So, we do not know the nature, we are not commenting on the nature of the body force, we are just putting it as x, right. So, these are basically the forces that are acting on the control volume, right. So, that takes care of the first, if you look at your terms, this would takes care of the sigma Fn, right, these are the forces, right. Okay. So, similarly now that you have done the forces, let us look at the mass now, momentum in, momentum out, because that needs to be taken into account, because that is the other part of the puzzle, right. So, let us take the same control volume. I am not doing it in the same picture because of the simple reason it gets very crowded and messy, right. So, one thing is for sure that the momentum that is coming in, okay, is rho u square delta y, is it right. On the other side, the momentum that is leaving the control volume is rho u square plus, once again the Taylor series expansion comes into the picture, it is given by rho u square divided by delta x to dx into delta y, right. You understood this part is very simple. Rho u is basically the mass, rho u into u is basically the momentum, right. So, that is the momentum flux that is coming from inside the control volume. So, that means that is momentum in, this is actually momentum out, right. Is that all? It is actually not the case, because there is also mass which is entering into the control volume from the y face, right. It is, there is also mass, and what is that mass that is entering into the y face is basically rho v, right, into delta x, am I right. Okay. Now, that particular mass can be carried in the x direction with a velocity u, right. So, in that particular case what will happen is we will have u v into delta x, right. So, this is the mass that is carried in the x direction, right. Similarly, there will be mass which will be exiting the control volume, but they may be washed away by the u component of the velocity. So, that will be given by rho u v, that term is common, plus once again the same Taylor series expansion of the whole thing dy rho u v, okay, into delta y, the entire thing is multiplied by delta x, got it. Okay. So, in the x direction, when you look at the x direction momentum equation, these are the two principal players, this gives you Fn, or in this case Fx, okay, and this gives you the m, the momentum flux essentially, right, okay, that is coming in and out, right. So, now what we do, we can assemble all these terms together, okay, and look at the individual parts of their share, right. So, for example, on the force side we will have a share, on the momentum flux side we should have a share, right. So, what will be the share on the momentum flux side? It is once again momentum in minus momentum out, it is a very simple thing once again. So, if you do that, then what you will get? Right, okay, minus Okay. So, this is the momentum basically in minus momentum out, got it. On the other hand, delta Fx on this side, what that will give you if you expand the whole thing once again. I am not going through all the steps, this you can work out as homework if you want to just go through all the steps, but I have given you the basic. It is basically subtraction, it is basically algebra. Okay. So, sigma x by delta x into delta y, okay, plus x into delta x into delta y, right. So, this is the Fn terms that you are going to get. So, you have this Fx and then you have the momentum flux term, right, on the two sides. Okay. Now, you are left with only one thing, that is the change of momentum within the control volume. And what is the change of momentum within the control volume? Okay. What will be the change of momentum within the control volume? That is the thing that we are going to look at. Okay. So, remove this one. Okay. So, now that we have established that what is going to be the situation. Okay. Now, the rate of change of momentum within this control volume, let us go back one slide up. Okay. So, if I draw it here, I think it will be more visible, right. So, if you look at the that is the rate of change of momentum within the control volume, right. It is rho u into delta x delta y. This is the x direction, of course, okay, because once again the direction part is very important here, right. So, if you assemble all the terms now, that means we are gathering now all the terms, right. Your equation would look like, and once again I am doing it in 2D. 3D is no big deal, you can just have to do a little bit more algebra than what is required. Rho uv is equal to x plus d tau yx by dy minus d sigma x by dx, right. Okay. That is what you get. Now, you can simplify things a little bit. Okay, you can, I mean, there are terms which are within the bracket. So, you can basically unfold them a little bit. So, what you will get is u d rho dt plus rho du dt plus u d rho u dx plus rho u du dx, okay, plus it is a long expression basically, rho v du dy is equal to x plus d tau yx by dy minus d sigma x by dx. Okay. Now, you just gather the terms where the rho can be taken out, dt plus u du dx plus v du dy. Okay. The other term, why it will cancel, I will say in a second, tau yx by dy minus d sigma x by dx, right. Now, if you look at that, what happened to the other term that we kind of dislodged, if you can see that the term with that really did not pay any attention to was basically already incorporated in the continuity equation. So, that term basically goes to 0, right. So, this is the only term that actually survives. Okay. So, if you do a term by term comparison, this term survives, right, this term survives, this term survives, correct. Okay. This term will survive. Okay. What about the nature of the other two terms? Because if you take u out of those terms, this term, I am putting two symbols over here, this particular, not this particular term, I am sorry. Okay. So, that particular term, this particular term, okay, and this particular term will actually go to 0 if you add them. That is the basically the continuity equation that you have, right. Okay. So, this is the full expression that you will get. This is what we call the convective acceleration term. this entire thing. This is the body force term, right. This is basically the surface force terms, and these two are basically both are surface forces in a way. Okay. So, this can be also compactly written in terms of the material derivative, right. This is once again in the x direction only. Of course, y direction will be very similar to this, but y direction is something that we are not really bothered about right now, because that will be essentially the same. Now, looking at this particular last expression over here that you have, you say that this does not look anywhere like the equations that we are most familiar with, right. Okay. So, what is the most common equation in fluid dynamics, right? That is given by the Navier-Stokes equation, right. This does not look like Navier-Stokes equation though, right. Okay. It does not look, because the where are the forms, okay, where is viscosity, where is all these terms. Now, to answer those questions, this is the most generic form of the momentum conservation equation. We go to the Navier-Stokes equation only after we have taken into account certain constitutive relationships. Okay. After we know the constitutive relationships, then only we can go and migrate to the Navier-Stokes equation. So, that is the most important thing to note in this particular thing, that we have to now apply certain constitutive relationships to know. For example, we do not know what is the nature of tau yx, what is the nature of sigma x. Okay. Somehow you have to relate this, you know, to the pressure, to the velocity field. Okay. Unless you can relate them, okay, this equation you cannot solve in that particular fashion, right. Now, most of you must have heard things like, you know, Newtonian fluids, non-Newtonian fluids and things like that. All it does is basically you have to cast these stress terms essentially, and the body force term also, because body force can also have variety of forms, but that is relatively intuitive. You know that gravity is the most commonly encountered body force. So, in order to cast this in terms of the body forces, all right, or cast the surface forces in terms of certain known field quantities, is what the purpose of the constitutive relationships will be, right. And that will actually reduce the problem to the more manageable Navier-Stokes form that you are most familiar with. Okay. So, let us look at the constitutive relationships. Okay. So, the first constitutive relation is sigma x, right, that is the normal stress, is given by the pressure minus 2 mu du dx plus 2/3 mu du dx plus dv dy. Got it? That is the first term. Then tau yx is the same as tau xy, right. This is the stress, the shear stress tensor. Okay. Now, you guys are all familiar with tensor notations perhaps, right. So, that is a tensor. So, that is given by mu du dy plus dv dx. So, these are the cross derivatives of the velocity. That is the change of u velocity in the y direction, change of y velocity in the x direction, that is what it is, right. Okay. So, this is basically what is the Newtonian fluid concept, or Newton's law of viscosity, the second relationship that we have put forward over here. Okay. So, this essentially means that there is no resistance, okay, to change in shape, right. Okay. And but it resists the time rate of change of shape, the time rate of change in shape. Got it? So, these are the two important things to note. No resistance to change in shape, but resists the time rate of change of shape. Okay? Time rate of change of shape. Okay? Now, for incompressible flow, once again, now these are the special assumptions for incompressible flow, okay, with constant viscosity. That means the viscosity does not change, okay, with space. There can be fluids where the viscosity can change actually spatially, okay, or with the flow field. Okay. So, there what we get is basically dv dt is given by is basically the body force. So, we have reduced this using the constitutive relationships and for constant viscosity, this is the term that you are most familiar with. This is the Laplace of the velocity field, okay, which is basically the viscous terms, right. These are the viscous terms, which is viscous stress, which is basically the shear stress, okay. This is basically the pressure term. Where does it come from? It comes from here, right, and this is basically your convective acceleration. Right. Okay. If you look, when you are using incompressible flow, this particular term actually goes to 0, okay. That particular term actually goes to 0, got it. Okay. So, if you do the math after that, you will get that this is the most compact form of this equation, right. Now, mu v, right, which is basically the viscous term, right. Now, for the x direction, it can be written as u, right, which will be mu d square u dx square, right, plus d square u dy square, right. So, that is basically the Laplace of the velocity field, right, and this is the body force term. Most of the time it will be like rho g, which is basically the body force if the g direction and the x direction actually matches. Otherwise, it will come in the y component of the velocity, right. So, this is of course the total equation, the total equation form. Now, it v will become equal to u or small v depending on which direction you are applying the momentum equation with. So, this looks very familiar to you guys, right. So, all we have done is that we have taken a control volume, infinitesimal control volume, we have applied the conservation of momentum, and by using the conservation of momentum, what we have achieved? We have achieved that the rate of change of momentum, okay, is equal to the momentum in minus momentum out and plus the whatever the body forces, whatever are the body and the surface forces, right. So, the surface forces we already saw, they were the normal stresses and the shear stresses. Body force was basically the gravity and similar stuff, okay. So, after we have derived that, we have gone through the constitutive relationships, okay, and one of the constitutive relationships is Newton's law of viscosity, right. So, for Newtonian fluid and other things, we have been able to prove, right, that this will be the form of the equation that you will get, okay. For incompressible flow, constant viscosity, Newtonian fluid, using the constitutive relationships that we just laid down, you would be able to show that this is the entire relationship which has got a pressure term, a viscous term. Remember, this is not just the pressure, this is the pressure gradient, okay, which is important, right. And then you have the viscous term, you have the body force term, and you have the term which is related to the convective acceleration, okay. So, this particular equation takes care of the flow field. So, therefore, when you have a flow field over a flat plate, using this equation over there, right, technically you will be able to solve the velocity profile, and the velocity profile in this case will look something like this, that we will come a little later, okay, that what the velocity profile should look like. But this equation should suffice. Should you be able to apply this, you should be able to get the flow field information naturally coming out of this, right. So, why I said this was important? Because you need to solve the momentum equation before you go to the energy equation. Energy equation is nothing but conservation of energy. This is the same equation that you saw in your thermodynamics course, right. But before that, you need to know what is the flow field nature. As you saw, the flow field here, it's for example, V is the flow field, right, the V is the velocity, depends on so many interplay of so many terms. There is a viscous term, there is a pressure term, there is a force field term. So, all these play a role, okay, in resulting in a spatiotemporal variation of the velocity field. Spatiotemporal velocity field means that V is as a function of x, y, z and t. Right. So, that velocity field we should be able to identify through this, got it. So, what we will do immediately now is basically we are going to look at the third player in this, okay, which will be the energy equation, okay. So, energy equation, why the energy equation is vital? Because of the reason that we said that energy equation is nothing but the first law of thermodynamics. first law of thermodynamics. That means this is the first law of thermodynamics. What does first law of thermodynamics say? It basically says energy is conserved, right? It is nothing more than that. Energy is conserved, right? So, and that energy conservation we have to going to write it in a slightly different form in a field form essentially, right? So, the energy, so what we will do, we will take that same control volume and we are going to work out the math on that. So, we are going to first look at, say if this is the control volume, once again there will be some energy that will be coming in, there will be some energy that will be leaving out, right. So, the energy coming in, say it is rho u e, that means the flux in the x direction is carrying this much amount of energy into the, and E is basically the internal energy, right, and then there is a delta y. Okay. On the other side, if you just do the Taylor series expansion for that, okay, you will get d by dx rho u e into delta x to delta y, right. So, that is the energy that is going out. Similarly, there will be energy that will be brought in by this vertical stream, right, which will be rho v e into delta x, and what will be coming out will be rho v e plus d by dy rho v e into delta y into delta x, right. Okay. So, this is the energy that is coming in, this is the energy that is going out, this is the energy that is coming in the x direction and it is being taken out, though energy is like mass, right. So, essentially whatever the momentum is, whatever that mass is bringing with it a certain amount of energy associated with it, right. There is a blob of mass that is flowing in, it carries with it certain amount of internal energy, that is what we are actually budgeting for here. Similarly, there will be a change of internal energy within the control volume, which is rho e into delta x into delta y, correct. That is the rate of change of internal energy within the control volume because of all these flux terms. It is essentially the same concept, energy in minus energy out is equal to the rate of change of energy within the control volume. That is what you are most familiar with. E is basically the specific internal energy, right. We do not know what that is, okay. So, but from thermodynamics you are very familiar with what is called specific internal energy. So, this particular expression basically lays down like mass, it is ME basically, mass into whatever. So, specific, that is why it is specific, it is an intensive property, right. So, you multiply it by the mass, you get the total energy that is flowing in minus that is whatever is going out. So, in the next lecture what we are going to do, we are going to take this premise that we have already laid down, very similar to your mass conservation, and we are going to see that how you can convert this to a temperature field, because that is what you need, okay. That is the quantity that you can measure. Internal energy is not something that you can measure, right. So, in order to cast it in terms of the temperature field, because that will lay down now the foundation that you know the velocity field. Now, if you know the temperature field, you also know the continuity, you would be in a position to solve all the problems later on, okay, using these equations, okay. So, that is what we are going to do next class, okay. So, last class we laid down the foundations that how the internal energy, I mean the control volume approach and how it can be used to basically cast the conservation of energy. Now, if you look at this particular control volume, okay, now you want to cast it in the form of heat first, okay, or the heat fluxes. So, let us write the conservation equation in a slightly more rational form. The rate of change of internal energy inside control volume is equal to net transfer of energy by fluid flow, right, which we covered in the last class, that was the fluid flow, that means energy that is brought in and out, okay, plus the net energy transfer due to conduction, okay. Conduction means it is diffusion, that if how the energy will be transferred, plus rate of internal energy generation. Now, this can be important. What we mean that within the control volume, say for example, we have some source of heat okay, which is generating energy. So, that is also possible, okay, okay, and then minus the net work transfer from CV to surroundings. Got it? So, we basically in the previous slide, if you or in the previous class what we did, you saw that this was the expression that we laid down. So, this was basically the energy which was transported due to flow, right. So, we covered one basis of this, right. So, that is the first thing that we covered, that this is due to flow, what is the energy that is transferred, right. Now, what is the net energy that is transferred due to conduction? Let us look at that particular part of the problem. So, here it is Q xx into delta y, where Q whatever it is, Q I is basically the heat flux in ith direction. Got it? Right? And it is leaving the control volume with Qx double prime plus dQx prime divided by dx into delta x. Okay. This entire thing is multiplied by delta y. Got it? So, that is the other term. Okay. So, similarly you have Qy into delta x, whatever is coming out from the other side of the control volume, Qy double prime by delta Qy double prime by dy into delta y to delta x, right. It is a little bit messy the way, but I think you can still identify that. So, this is basically, and there will be heat generation within the control volume. So, that is given by that. So, that is this, we have covered this term now, this entire thing, plus what is the rate of internal energy generation. Got it? Okay. So, generation or dissipation, it can be a sink also. Okay. So, depending on, it can be positive or negative, right. So, positive can be positive, you put a plus sign, negative can be negative. So, you understood. So, this is the basically the heat flux in the x direction, this is the heat flux in the y direction. Heat flux in the x direction comes with it you once again do the Taylor series expansion and you got that. Okay. Similarly, the heat flux in the y direction, you once again do the Taylor series expansion and get that, right. So, entire thing if you now put it together, okay, what it will look like? It will look like rho E delta T delta x into delta y, right. That is the rate of change of internal energy within the control volume, d by dy rho V E into delta x into delta y, right. That is what we got from the net transfer of energy by fluid flow, right. Okay, minus, and I have taken into account all the negatives. That means you basically simplify the form. I am not showing the steps for the simplification, that ideally you should practice, okay, plus Q triple prime, which is basically the rate of generation or dissipation, minus dQx double prime by x plus dQy double prime by y into delta x into delta y, okay, plus there is some work term which is given by delta x into delta y, right. So, the work term is whatever the work that is done to the surroundings, or the surrounding does work on the body, okay. So, this is the full expression. We have just assembled all the terms now. These came from the flow, this came from the conduction part, this is basically the work part, and this is the rate of change of internal energy within the control volume, right. Up to this I think it should look pretty familiar, right. Now, we can go on simplifying the thing a little bit more. So, d rho E by dt plus rho V E plus d by dx rho U E is equal to Q triple prime minus dQ double prime dx double prime dy plus this W, right. So, I have got rid of the delta x and the delta y kind of term, right. Okay. So, the work What is the nature of the work? Okay, let us look, because that W is something that we need to have a handle on, right, that what is that W. Now, if you take the control volume together, right, so the work transferred by normal and tangential stresses, right. What else the work can be? It will be the work that will be covered by the normal and the tangential stresses. These are the two forces that are acting on it. So, these are the ones that should be doing the work, right. So, the work done by sigma x is basically the normal stress that needs to be evaluated, right. So, that work done should be something like sigma x into delta y into 1, right. So, that will be the work done. Okay. So, similarly so this is the value of the work that will be done by the normal stress. Okay. So, similarly, if this is phase 1, this is the work that is done. If this is phase 2 of the control volume, what will be the work done on that particular phase? That will be sigma x plus d sigma by dx into delta x, right. Right. So, that is the other part of the thing, and that it will do a work, sorry, delta y, that should be the other part of the work that will be done on phase 2. This is 2, this is 1, this is the phase though, right. Okay. So, one of the work, so this will be the other part of the work. Okay. So, now is this going to be all, or is there a unit problem that we have over here? So, as you can see that though this gives you the force, this is basically the force, right, this is not the work, right. So, this is the force that is acting on phase, this is the force that is acting on the other phase, right. So, how do you get from force to work? You basically have to multiply it with some kind of a velocity scale in this particular case, right. So, in this particular case, the velocity scale, we have a ready velocity scale which is u, right. So, for this particular work, the total work done on phase 1, right, will be sigma x into delta y into 1 multiplied by u, right. On phase 2, right, the total work will be sigma x plus d sigma x by dx into delta x into delta y, right, multiplied by u plus du, okay, by du dx into delta x, correct. So, this is the work that is done on phase 2. Am I right? So, these are the forces, this is basically the work, correct. Okay. So, once these work paradigms are kind of leveled out, now what we can do, similarly there will be expressions for shear stresses as well, all right. These are for the normal stresses. Similarly, there will be expressions for the shear stresses as well. Not going to go through the whole thing, but let us put the final expression for W that we have. It will be sigma x into sigma y. This is all the terms combined. Once again, you should take the effort of going through each and every term and try to work out that how this is coming. Plus is a long expression dy got it. There is a full expression for the work, right. Okay. This is the full expression for the work that is done on the thing. Okay. Now, you should also spend some time thinking that what will be the sign of these quantities. I have given you the final expression, but this is left as an exercise to the to all the participants, that what will be the sign of this, will this be positive or negative. Okay. I have given you the final expression, so you can see that what the sign, ultimate sign will be if you work through the steps, but then you have to understand, get a feel that why one should be positive or one should be negative, or is it both should be positive or both will be negative, that you have to kind of find out from this. Okay. Now, you have a huge expression for this. Okay. You have a huge expression, but fortunately or unfortunately you will find that most of these terms are basically does not make much of a contribution. Okay. But it is important to know what is the nature of these terms though. Okay. So, that is what we have done. Okay. Now, going back to the original formulation, and we will keep W as is, we are just breaking up the whole expression. Let us put this properly so that you can see. Okay. This I have written W. W is that expression that we wrote in the previous. This what we have done is that we have basically broken up the whole expression into a series of individual quantities. Okay. Unfolded it once again. Now, if the flow is incompressible, that is what our main conjecture was, and what I said that most of the course will be on incompressible flows. Okay. For incompressible flows, okay. So, that is the expression that you get, okay. Or if you can write it in a more compact form, plus W, right. So, W is that big expression that we wrote. You can technically show that the W, if you work through the math once again in the previous page what we showed, it is actually written by P into the divergence of V plus a quantity called mu into phi. Okay. What is phi? Phi is basically 2 into du dx square plus dv dy square plus du dy plus dv dx square. Got it? This is all can be derived from the previous expression that you had, you just have to go through the steps. This is what we call viscous dissipation. Now, for an incompressible flow, this first term will basically go to 0, right. Okay. But the first term will go to 0, but the viscous dissipation term, depending on the flow that you are dealing with, may or may not actually survive. Okay. So, may or may not, that is the key important part, right, that if you are dealing with flows, say for example in very constrained geometries, that means when there is a large, say this is a channel, there is a large flux, okay, or a high flow rate through a very constrained channel, high aspect ratio channels, viscous dissipation can become a very key quantity. Okay. So, especially in lubrication and other places also where the viscosity also, there are two parameters as you can see. One is viscosity can be very large, that can lead to a high level of viscous dissipation, right. Okay. That expression can actually go up, or your velocity scales has to have a very strong correlation, and it is always the squared quantity that you can see over here, right. All these quantities are squared, that means this is always positive, phi is always positive, right, because it is always squared no matter what is the gradient, okay, it is always squared of the gradient, right. So, it is always a positive quantity, that is the first thing. And second, if you look at, these are basically all the slopes, this is the slope of velocities in different directions, right. So, it is the slope of u velocity and v velocity in different directions. So, if the velocity gradients are very sharp, that means there is suddenly a sharp decay of velocity or a sharp rise in velocity, you can actually increase this phi. Okay. But remember, it is a squared quantity, so the effect is actually kind of minimized. Okay. But if you have a sharp gradient anywhere in the flow field, you can actually generate a lot of this work. Basically, through work you can generate this viscous dissipation. If your viscosity is high, it can also have effectively the same effect. That means, if you try to push a very viscous fluid through a very narrow opening, you can actually generate a lot of heat. This is sometimes what happens in kind of lubrication, in bearings and other things. Things can get hot also. Okay. So, that is the expression for that. Let us look at now the next one. Now, we have this expression, the combined expression. Okay, into phi. Okay. So, now in terms of enthalpy, so enthalpy is some quantity that we are very familiar with. So, enthalpy is basically E plus P by rho, right. Okay. So, dH by dt, right, will be dE by dt plus 1 over rho dP by dt minus P by rho square d rho by dt. See if you understood, right. Got it. So, this is just a simple expansion, that is what we did over here, right. Okay. Or in other words, rho dH by dt minus dP by dt plus P by rho d rho by dt is equal to q triple prime minus delta double prime, okay, plus mu to whatever is the viscous dissipation term, right. Okay. Now, okay, so dH by dt, you can just take this dP by dt, you can take it to the other side, plus q triple prime minus u double prime, right. And we obviously know that since it is incompressible, right, the rho is not varying, right. So, that other term goes to 0, okay, that d rho by dt term that is there, that goes to basically 0, correct. So, based on this, this is the expression that you are going to get, right. So, this casts is in terms of the enthalpy, right. So, the enthalpy, this is the generation term, this is basically the diffusion or the conduction term, okay. So, to say this is basically the viscous dissipation term, this is like the pressure term that we have, right. Now, what we can do to get rid of this q double prime, there is a ready-made avenue, right, in conduction literature. If you look at it, it is called the Fourier's law. What it gives is basically q double prime is basically minus k into the gradient of temperature, right. So, this is, in other words, is known as the Fourier's law, correct. So, therefore, what we have is dH by dt k dt q triple prime right. All we have done is that we have replaced now q double prime as a heat flux with the equivalent temperature field coming from where? The Fourier's law of heat conduction. This you already know, and there is nothing more to say about that, right. But still, if you see, if you look at this equation, there is an interesting problem associated with it. We still have H, which is hovering around, there is T over here. Of course, these terms are still kind of dependent on the velocity field, as we can see, right. Here the velocity field is already hidden in the material derivative, right, because dH by dt is nothing but u dt, I mean you can expand it in the full form and you can write it that there is a velocity component, or the velocity components are already hidden here, right. So, but still that H needs to be cast in terms of temperature somehow, right, otherwise this does not make much of a sense, right, because enthalpy is not something that you can solve that easily, okay. So, what do? You already have dH equal to TdS plus 1 by rho dP. This is already known, right? You already know this, correct? Okay. Now ds, which is the entropy, it can be written in this particular form. If you are not familiar, please look at the Maxwell relations. Okay, so this is how it is written. Now from Maxwell, these are the Maxwell relations, extremely powerful. Okay, so ds by dp t is actually given as nothing but beta by rho, where beta is basically 1 over rho into d rho by dt at constant pressure. Right. Similarly, ds by dt at p is given by Cp by T, right. This is Maxwell relation, right. So dH therefore can be written as, because we know already, we wrote this particular expression in this particular way. Okay. So as you can see, therefore dH can be written, if you substitute quantity by quantity substitutions, if you do, because ds we have already cast it in this particular form, is basically Cp into dt plus 1 over rho 1 minus Bt into dP, right. Okay. Therefore rho dH dt, the rho Cp dt by dt plus 1 minus beta t into dP by dt, all right. That is what you will get. Okay. Now we are in a perfect situation now to cast it in terms of temperature now, which will give you rho Cp in terms of temperature. Okay. Now for incompressible flow, beta is equal to 0. Okay. For ideal gas, however, beta is equal to 1 over T, right. So for incompressible flow, whenever we say that beta equal to 0, that is because density is not changing. So naturally the beta will be equal to 0. So as you can see, that moment that particular thing happens, okay, this entire problem now is a highly tractable problem that we see over here. If beta is equal to 0, so therefore this term will drop out. You will get the very familiar expression dt by dt is equal to 1 over rho Cp. Okay. If k is constant, you can take k out. So this will be given in terms of the Laplace of temperature, and if the heat generation term, either it can be 0 or it can stay, plus mu into phi, both divided by rho Cp, correct. Okay. Now k by rho Cp is basically given as alpha, which is basically nothing but the thermal diffusivity of the system, right. So it is basically dt by dt is equal to alpha into del square by T, right. Now in most of the cases you will find that when there is no heat generation, that term goes off. When there is no viscous dissipation effect, that term also goes off. So this is the most familiar expression that you have kind of familiar with, which is basically, this is the convective term, this is basically the diffusion term, right. Okay. So as you can see, we started with the conservation of energy equation, we slowly took off certain terms, and we showed that the final most simplistic version is given by this. Now there are other versions which are given in this particular form. This is the most generic type of things, but you can take off quantities, okay, depending on your requirement, your flow field. It does not say that this is the universal relationship, this is not the universal relationship, right. The universal relationship you have to start a lot earlier, right. Here there are a lot of assumptions that we have made before we got to the final form. So that is the final form that you will normally encounter in this particular course, okay, and that is the expression that we will use. As you can see, u or the momentum feeds into this material derivative, right. So, you need to know, you need to solve the u or the velocity field to compute what will going to be the temperature field. So, in the next class what we are going to do, now that we are done with the conservation equations, okay, we are going to look at the first set of canonical problems, which will be the flat plate. Okay. Thank you.